Hey, I got a haircut. I went to one of the great clips. Have a coupon, and I could have asked them for one. They didn't,
They didn't give out.
But they so I went there. It's like one of them. There was only one person. No, they didn't even show up on Saturday. It's like really, the weather wasn't that bad. And so I went on Sunday. There was one person there, and it said wait time 141 minutes. I thought, what? Are you kidding me? Okay, so I went to a different one, and we got in about 15 minutes. All right. Well, anyway, I want to show you where we're doing here. I had mentioned to you that this chapter is clearly, it has aspects of it that is truly an honors class chapter. And this right here is not even in the chapter. That's why I'm going to ask you to, if you happen to have your books with you, we're going to go way over here to that's chapter 15. And I really like the author of the book, but I think it would have been nice for him to have this picture way back in chapter 7. And we saw a video of this, and I'm just going to show you the highlights of this again. In case you weren't here, if you haven't watched the video, I did give you points for taking notes. If you weren't here, you can watch the video. Just give it to me sometime this week, and I'm not going to count it late because I know some of you were out last week. Okay, but anyway, this chapter has, I think, some high-level stuff in it, and I only teach a little bit of this chapter to the non-honors class, just a tiny bit of it. So I do know you guys, I want to ask you to do your best, and I know you can, and you'll, if you can do well in this chapter, you're a pretty good student. So anyway, let's take a look, and the first thing we found out was that water has a lot to do with this chapter. It's called reactions in an aqueous solution. So that means it's dissolved in water, doesn't it? So what we're going to do here is take a look at water. All right, number one, I mentioned this to you before. If water didn't act unlike almost anything else on the planet, nothing alive would be here. No life would be here. The planet would not be the way it is. It's really, really unusual. Water is much more unusual than you think. And we don't really see water in huge abundance anywhere else except on the earth. And so it's really crucial. And so let's take a look at the chemistry of water a little bit. First of all, this is called a bent molecule, and it's not linear. It's not straight. If it had been straight, like HOH, like that, we wouldn't have all the stuff that we talked about. So number one, it's a bent molecule. And what kind of a bond would hold hydrogen and oxygen together? It's a non-metal. Are they gonna form ions, metal, like metals and non-metals? No, so it's gonna be covalent, isn't it? Now, so that's neat. That's covalent bonding. So they're gonna share a pair of electrons. One of mine and one of yours. One of mine, one of yours. They're gonna share that pair. And I mentioned the other day, did I use the Snicker bar analogy the other day?
Yeah,
Okay. So here, I even drew it here. So if I cut off a teeny piece of the Snicker bars and I give it to Fiona, I don't know if she likes Snickers, but she can't say anything. I did share with her, didn't I? It's you that thought sharing had to mean equal sharing. Are there some elements that share equally with another element? Yeah, but not in this case. Oxygen is more greedy, or they call it more electronegative. And so when we share a pair of electrons, these negative electrons spend more time around oxygen. So what happens is one end of the water molecule has a slight negative charge. And what about the hydrogen end? Slight positive. So what do you call that? What do you call the molecule that has opposite ends, positive and negative? A polar. Okay, now this bond is a polar covalent bond, but the molecule itself is also polar, and that's really what makes the difference. So let's take a look. Have you heard the word inter, the Latin prefixes inter and intra? Have you heard that before? We say inter means in between, like intercollegiate athletics. What's that mean? Like intercollegiate, right? Wouldn't it be like Wake Forest playing state or something like that? Okay, but what if you went to Wake Forest and they had intramural athletes? Who were you playing there? You wouldn't be playing people between different schools. You'd be playing within the same school, wouldn't you? So intra means within. So what kind of a bonding holds water molecule together? What's the intramolecular bonding of polar covalent bonds? Okay, that's nice. But now, what happens when you get a water molecule next to another water molecule? What would happen if you get a water molecule next to another water molecule? And we talked about this the other day. What would happen if you get a water molecule next to another one? And these are slightly negative, slightly positive. So what about another one comes in here? Which part of another water molecule would be attracted to this part here? Which part? The hydrogen end? Okay. So I'll even draw it here. Okay, now, so what do you call what about the intermolecular? What is the intermolecular? Is there a name for that? And that was on the video, and what do you remember them calling that? What do you think? Do you remember anything? Reese, you remember that? I know it was last week. Okay, so they had a name for this, and the kind of bonding that is intermolecular is called hydrogen bonding. All right. And what's the intramolecular bonding called? Polar covalent. That's it. Everybody got that? Okay, so if you remember that video, they made a big deal about hydrogen bonding. And when water, for example, I'll show you in just a second here, and that's what makes this chapter a little bit higher level. I'm going to show you something here that I'll get into even some physics here. I'm going to show you, let's see if the camera can get here. Here we go. All right, so here's a little physics equation, and I know this is Monday morning. You say, wow, I'm taking a chance trying to teach a little physics too Monday morning. But in physics, if you want to find the kinetic energy, did you have that in middle school? The kinetic energy is energy of motion. Did you remember anything like that? Like you have potential energy and a kinetic energy. Okay. So kinetic energy is the energy of motion, and in physics, it's 1/2 mass times the velocity squared, if you want to calculate it. Same thing with a car. If you want to know, for a car, what's the kinetic energy of a car? It's 1/2 the mass times the car times the velocity squared. Matter of fact, police, they do this. They'll go to a scene of a crime, and they'll actually look at it, and they can take some data, take it back, put it in a computer, and even though they're not physics majors, the computer will tell them that car was going more than 70 miles per hour. How would they know that? Because that's how much kinetic energy the car had. When you were taking, how many of you took driver's ed yet? Okay. Do you remember driver's ed? They had maybe something like, let me do a little drawing here. In driver's ed, they had a thing where they said, if you're going at 10 miles per hour, how long would it take you to stop your car? Do you remember that? And then what if you were going at 20 miles an hour? So this was 10 miles an hour, and here's 20. And what was it? Wasn't it twice as long? No, it wasn't. It was a lot longer. And as a matter of fact, if you went to 30 miles an hour, it was a lot longer. So what were they? They didn't want to teach you the physics of it in driver's ed. They didn't want to teach the physics of it. They were just trying to tell you, the faster you go, it takes a whole lot longer to stop that car. Why? Because you have to get rid of the kinetic energy of the car. How? Well, friction, mainly friction, and it takes a certain amount of time for frictional forces to take away that kinetic energy. And so the reason they never told you the physics behind it, but it's that equation right here, kinetic energy equals 1/2 mv squared. And so what that means is, if you're going twice as fast, then square that, you have 4 times more kinetic energy. If you're going 5 times faster, you don't have 5 times more kinetic energy, you have 5 squared, 25 times more kinetic energy. Sometimes you hear about asteroids, an asteroid the size of a city. And, so what? So what? It's not that big compared to the whole Earth, is it? But you know what it has? It's going fast. It's going fast. and it starts coming to the Earth, it's going to even go faster. So how much kinetic energy would that thing have? Huge, huge amount. And that's what they're talking about, asteroids that have the potential to, destroy a planet, wipe out life, that kind of thing. It's not because just that little, it's not only this big, it's the kinetic energy that it's going to give off. All right, well, anyway, the reason I want to show you that is, now see if you can stay with me on this, all right? I want to show you, I'm going to talk about something, think about, I don't think the camera's showing this very well. Think about this little gas here. See H2? How much would H2 weigh? Let me show you. An H is about 1, and H2 would weigh about 2. So its mass is about 2. Now, room temperature has so much kinetic energy already that if you only have a mass of 2, that you going to have so much kinetic energy that you cannot be a solid, you cannot be a liquid, you have to be a gas. Does that make sense to you? Hydrogen has to be a gas at this temperature. Well, let's go something like, how about something like O2? How about O2? How much would O2 weigh? Well, one O would weigh 16, 2 of them would weigh 32. Well, that means, wow, if your mass gets bigger, then you're going to be moving slower at the same temperature. So now these oxygens are going to be moving slower than hydrogen, but guess what? How much, is that enough kinetic energy for oxygen to be a liquid or a solid at room temperature? No, it's not. If you weigh 32, you're going much slower than this guy here, hydrogen, but you're still moving fast enough that you have to be a gas. Let's go to CO2. How much would CO2 weigh? Carbon weighs 12, 2 oxygens weigh 32, that'd be 44. You weigh a whole lot more. You'd be going even slower than O2, but what is CO2 at room temperature? It's a gas. Let's jump all the way to this one. This right here is called butane. Butane lighters, that kind of thing. And its mass is 58. Now that's going to be moving even slower. But what is butane at room temperature? It's a gas. Now, what's the bottom line? If you have a mass that's not, even all the way to 58, room temperature is enough, you have to be a gas. You have to be. What's the mass of water? What's the mass of water? Look up there. H2O. How much? What would be the mass of a water molecule? How much? 34. Try it again. It's not H2O, it's H2O, 1. Yes. Yes, 18. 2 H's, 1 and 1, that's 2. And an oxygen 16, right? 18. So water has to be what? It has to be what at room temperature? Is it even 58? You have to be a gas. And what is oxygen? What is water? 18. So look at this. See right here. That shouldn't happen. That should not happen. Everything else, even way bigger than you, even way bigger than water, is going to be a gas at room temperature. So why is water? Why is water a liquid? What's the reason? And if you're here for that video, you should know. What do these other things not have that water does have?
Water has high specific heat.
What is it?
High specific heat.
Well, what is that water has that other things don't have? What would make water want to pull itself together into a liquid when it should be moving fast enough to never be forming a liquid at room temperature? And that's that thing up here. What's it called again? Hydrogen bonding. And so hydrogen bonding makes water, liquid water, exist. Matter of fact, I only know one substance on the planet that exists as a solid, liquid, and a gas, and that's water. You can go to the planets. I could go find maybe some solid methane somewhere, but I won't find all 3 phases. So water is so very special, and that's one of the things. Why is it that, I'm not going to get too much into physics of this, but when you start boiling things, if I were to boil some, maybe another material, it would boil at a certain temperature. But then this guy would boil, water would boil at a much higher temperature, because you have to overcome the hydrogen bonding before each particle can move fast enough to change to a gas. And that makes water have a huge range in which it can be a liquid, all the way from 0 Celsius all the way to 100. That's kind of rare for chemicals. Now, the reason I do want to impress upon you water's uniqueness, and I want to show you one more. Here's where we want to get in mainly to the chapter that you're doing right now. What would happen when I put NaCl in water? And we talked about this last week. We'll do it again. What is NaCl made of before I put it in water? Ions. Table salt has no neutral atoms in it. Everything in table salt is positive and negative ions, and they have the same number of each. That's why it's not charged. The whole thing's not charged, but it's made of ions. And is there an attraction between the sodium and the chloride ions? Yeah, opposites attract. It's called an ionic bond. So why would I put it in water? Why would it want to? What happens to it when I put it in water? Well, which end of the water molecule would be attracted to the chloride ion? The hydrogen end, right? Because it's positive. So it would go up here and say, I want to pull you out of here. And the other sodium says, no, I want to pull you in here. Okay, then another water, and another water. And after a certain number of waters get in there, who's going to win? Is water going to win? Or is NaCl going to win? Water. And so then this thing starts coming apart. The ions come out of the crystal, and they are surrounded. And can everybody see this picture here? I know it's right on the edge of the paper. Can everybody see it? And so the Na, the chloride ions, are all surrounded by water, and the Na ions are all surrounded by water. And that's what happens to ionic compounds that do dissolve in water. They actually come apart into ions. Do you understand how this is a little bit higher level chapter? Now, sugar is made of C, H, and O. What kind of a bond do you think holds C, H, and O together? There are many bonds, but what kind of bonds hold non-metal? Covalent. So what's sugar made of before I put it in water? Don't say ions. They're made of molecules, aren't they? Now, we're going to talk about just a minute why sugar dissolves also, but sugar will not break up into ions. It wasn't made of ions to begin with. So number one, here we go. Here's the bottom line. Why is water so, it's called a universal solvent. It doesn't dissolve everything, but it dissolves a lot of things. Why would water dissolve ionic compounds? Ionic compounds have a plus-minus nature, and what about water?
It also has a plus-minus nature.
It has a plus-minus nature, doesn't it? It's polar, isn't it? It's a polar molecule. And so likes dissolve likes, and so that's why we think water dissolves a lot of ionic compounds. Let's go over here, next page. Okay, now, you don't know, this is my first year chemistry, so take a look at this right here. This happens to be called ethyl alcohol. Okay, just alcohol. It's just the kind of alcohol that's in mixed drinks and things like that, okay? So this alcohol is made of carbon, hydrogen, oxygen. Okay, and that's fine. It's all covalent bond, But if you look at how it's made, do you see where O and H are right here? Here's carbon, hydrogen. You see where O and H here? I'm on page 463 right now, or just look at my picture. Do you see where it says O and H here? That's a covalent bond, but what happens when oxygen and hydrogen share electrons? Remember what happens? Who's greedy? Oxygen. And so this end will be slightly negative, and over here will be slightly positive. So guess what? Alcohol is not made of ions, but it also has it's a polar molecule. So it has a plus-minus nature in there. So does alcohol dissolve in water? Yes. As a matter of fact, when if you look at alcohols, if somebody goes to the ABC store and they buy something that says it's 40 proof, 40 proof, you cut that number in half, it means it's 20% alcohol, which is pretty high. Beer might be 5%, wine might be 12 or 13. 40%, 20%, that's pretty high. Matter of fact, you can get some that are 80 proof, 40% alcohol? That's way up there. You get that? So guess what? What if something's 40% alcohol? What's the rest of it? Water. So does alcohol dissolve in water? Yes, but would alcohol be an electrolyte? Would alcohol conduct electricity? The answer is no, because there are no ions to carry the charge. What about NaCl in water? Would that be an electrolyte? Yes, plenty of ions, right? All right, let's try one more. This right here, this is what you put in, you have at home. It's called table sugar. Table sugar is called sucrose. It's called C12H22O11. Non-metal, non-metal, non-metal. So what kind of bond holds this big guy together? They're all covalent. But guess how? Look over here. OH, OH, OH. Uh-oh. See that covalent bond? What's going to happen there? What's it called? It's going to be even sharing or uneven sharing? So right here it's going to have a plus minus nature, isn't it? So guess what? Table sugar is also a polar molecule. So does table sugar dissolve in water?
Yes.
Water's plus and minus. Table sugar's plus and minus. Yes, but would it be an electrolyte? No. Is everybody okay with this? This is getting a little higher level stuff, right? And I'll show you one more picture, and then we'll stop with this. I know you've known somebody in your past that says, well, you know, oil and water doesn't mix. They sounded just like that, didn't they? Even if it's your grandmother. Yeah. What would they say? Oil and water doesn't mix. What's that all about? Well, most oils are made of only carbon and hydrogen. Only carbon and hydrogen, which has a fairly even sharing of electrons, so it would be non-polar. Non-polar. So what do you think if I put non-polar things in water?
It's not gonna mix.
Not going to mix. And if it's less dense, it's going to sit on top. If it's more dense, it'll sit on the bottom. And it's not going to be electrolyte either, because I have no ions there. And so does that make sense to you? Water is great at dissolving a whole lot of things. It can dissolve ionic compounds. It can even dissolve some covalent compounds if they're polar. So it dissolves a lot of things. I don't know if you thought about this, but God made it so that water's not everywhere on the planet, but wherever it does go, it falls, right? And when it falls, it hits things like rocks and plants and dirt. And what do you think happens to it or runs across those things? Is it possible they could dissolve some of that material in the water and carry it down the stream into the river and make the oceans salty? And that's why we think the oceans are salty. Now, why do they become a little saltier every year? Because when water evaporates from the ocean, not salt water doesn't evaporate, only the water evaporates. And that makes clouds. Rain, more salt. Rain, more salt. And again, I'm not going to tell you that there aren't scientists that believe that the Earth is so many billions years old. That's fine. You can go to every museum and probably that's what they're going to tell you. But I can tell you also that if you just looked at the how much the oceans are getting saltier every year, if you did the mathematics there, the Earth couldn't be that old, or else something else happened completely differently. The oceans would be way, way saltier than they are now if you gave it that many years to rain and stuff like that. So there is evidence that shows that the Earth is not necessarily that old, and there's other evidence that says the Earth is old. Anyway, that's up to you. As you get older, you're going to have to make that choice, what you think about the Earth and the age of the Earth. A lot of you are going to say, well, yeah, I'll just say the billions of years, and when I go to college, they won't think I'm dumb, so I'll just say billions of years because that's what they want. That's what they say. But you can do that, but you need to look on your own evidence and figure out what you think. Is the Earth really, really old, like they said, or is not quite as old as they say, or maybe not very old at all? Okay. Anyway, now what I'm going to do is, do you remember this chart? Did everybody get one of these charts? Okay. If you'll come up here on this table right over here, there are two things that I gave everybody. I put them online, but you didn't have to print them. So take one of those. Okay. There you go. And then also, this right here is the homework for this afternoon. So last time we met, I asked you to look at this chart. There's a solubility chart for water. And I didn't want to tell you all the patterns here, but you actually figured out quite a few of the patterns. And here you go. Remember, these are the cations. These are all called salts. You know why they're salts? What are salts? Ionic compounds, right? And there are hundreds of salts. So here are your cations, your plus ions, and here are your negative ions. You put them together, you get a salt. Now, one thing you told me was that all chlorates were soluble. AQ means they would dissolve in water, wouldn't they? And then they'd all be electrolytes too, because the ions would come apart. You told me all nitrates were soluble, right? You told me that, it might be the other class. Another class told me that almost all phosphates are turned into solids. They're insoluble. And the only exceptions were ammonium, hydrogen, potassium, and sodium. And you told me that too. You said all potassium salts were soluble. All sodium salts were AQ. They would dissolve in water. And all hydrogen, that would be acids. All the acids are dissolved in water, right? Now, by the way, I'm not going to have you memorize this chart because I'll give it to you. You get it? I'll give you this chart. You just have to know how to read it. Okay. So then what we're doing is, this is a very helpful, I didn't say water dissolves everything, did I? I just said it dissolves a lot of things, and it does. So I want to show you a little, start something here. I'm going to do this on black paper, on black background here. Okay, let's try one. What do you think would happen? And if you have notes, go ahead and write this down. I'm going to react potassium nitrate, and everybody know how to write potassium nitrate? Now, ready? Potassium nitrate, AQ. What's that mean? Okay, so put potassium nitrate, AQ, plus sodium iodide, aqueous. All right, is everybody with me? All right, one more time. Everybody should know how to write potassium nitrate by now. Everybody know how to do that? Look at your neighbor, see if they did it right. Did they write KNO3AQ? Nitrates -1. What's potassium? +1. Everybody in here should have written KNO3 aqueous. All right, what about sodium iodide aqueous? Check your neighbor. How did they write it? Sodium's +1. What's iodide? What are all the ides? What are all the ides? Chloride, fluoride? Only when they're by themselves. What about when they're in a compound? What's sodium iodide? What's the charge on iodide? -1, isn't it? What's sodium? So you should have written NaI, aqueous. All right, what do you think is going to happen? Now this is what's going to happen on the next test. Is, whoops, you're going to give a chart, and the question will say, here's what the question will say. It'll say, if a precipitate will form, write the formula of the precipitate. Now let's go ahead and write this out, okay? This is a double replacement reaction. I'm going to go ahead. I want you to write out the formula for this, what's going on here, all right? Let's do it. So we got potassium nitrate aqueous plus sodium iodide aqueous yields. All right, what's gonna yield? Tim, you know, double replacement. Have you gotten the reactants? Do you have the reactants written down yet?
No, but I should.
Okay, that's what I asked you to do, okay? All right. All right, Daniel, what you got? Tell me the two products.
Products would be potassium iodide,
And how do you write that formula?
Ki,
Okay. And then what else? What's the other one?
plus sodium nitrate,
How do you write that?
NaO,
Oh, Na.
O,
What's nitrate?
NO3.
Okay, so NaNO3, right?
Yeah.
Okay. Does everybody have that? Okay, now, when we take a test, for today, you're not as ready as you will be. But is this reaction going to take place? Remember these things called driving forces? One of them is called the formation of a solid. Is a solid going to form here? So that's what we use this chart for. All right, look up potassium iodide. Now, since you guys are very smart, today I'll bet you're looking it up. But by the time the test comes, you'll say, wait a minute, I remember that all potassium salts are what? They're soluble, AQ, right? So they're not going to be a form of solid. So what are you going to write after the potassium iodide? AQ. Now, what about the other one? Sodium nitrate. You said today you're probably going to look it up. But by the time we do the test, what are you going to say? Wait a minute. I remember that all sodium salts are what? They're soluble. And you know what? You know what we put on this one? I'd put a big old NR. What's NR mean? No reaction. Now, before this chapter, you would have written this down and you would have said that's a chemical reaction. But now you didn't have the tools available to know that this reaction is not going to take place. You know what was in the beakers before you put them together? There was sodium ions, nitrate ions, potassium ions, iodide ions. And what is there after you mix them?
The exact same thing.
Potassium ions, iodide ions, sodium ions, nitrate. You see? No reaction. Let's try another one now. Let me try, let's try sodium iodide. So I write this one down. Sodium iodide reacting with lead 2 nitrate. How do you write lead 2 nitrate? How do you write lead 2 nitrate? What do you think? Let's see who got going. All right, Will. How do you write lead 2 nitrate?
PbNO3
Right. Okay, we need two of them, 2 nitrates, right? Now both of these are aqueous, aren't they? So did you write aqueous after each one of them? Okay. See what you look at your neighbor. See if they have it written down there. Sodium iodide, aqueous, plus lead 2 nitrate, aqueous. All right. Does everybody have that down? Look up there and see if yours match that. Is that what you have? Okay, now predict what's going to happen. What are the two products going to be? Zach, I don't call on you enough, right? What do you think? What's it called? Sodium what?
Sodium nitrate.
And how do you write sodium nitrate?
NaNO3.
That's right. And what's the other product going to be?
Plus lead iodide.
Which lead iodide?
PbI.
Which lead iodide?
Oh wait. Ev.
Which one? Lead 2 or lead 4?
Lead.
Huh?
Oh, lead.
Yeah, you start out with lead 2, it's going to be lead 2, okay? So lead 2 iodide. How do you write the formula for lead 2 iodide?
Isn't it like Ev?
Huh? Here, look right here. You said lead 2, so that's plus 2, right? Look up in the chart. What's iodine going to be? What's the charge on iodine going to be on a in a compound?
How do you know it's lead 2?
Oh, because over here, nitrate's -1. There were 2 of them. That means it's -2. So this lead is lead plus 2. Good question. Right? So it's lead 2. This was lead 2 nitrate, wasn't it? So this has to be lead 2 iodide. Now, what do you think? Is a reaction going to take place? You're going to look this up? You can. Or you can remember, not only are all sodium salts soluble, what else did you remember? All nitrates are soluble. So what am I to write after NaNO3? Aqueous. Uh-oh. Maybe it's another big NR. Now let's look up lead 2 iodide on the chart. Lead 2 iodide. All the leads are put together then. Iodide. Ooh, what does that mean? P. mean a little bit will dissolve in water, but most of it won't. So will it form a solid?
Yeah.
Yes. So I expect when I put these together, I expect nothing to happen on the first reaction. I expect something to happen on the second one. Are you ready?
So we put acid.
All right, in the first one, I expect nothing to happen. What do you see?
Nothing.
Nothing? Okay, and let's try the next one. I expect something to happen, and it did. Which one had a driving force that made the reaction take place? Second one. And the driving force is the formation of a solid. Now, this is a double replacement reaction, but there's another name for this kind of double replacement because the formation of a solid, what do you call an insoluble product? What do you call, here's the products, an insoluble product? What's the name of that? I always ask that on the test. Precipitate. This is called a precipitation reaction. It's also a double replacement reaction, isn't it? Yes, no?
Which one's it?
Is this double replacement?
Yes.
It is. Oh, by the way, we didn't balance it. Did we balance this yet?
Yes.
The first one is already balanced. What about this one?
No.
It's not. Okay, so let's balance it. That was easy. Is everybody okay? All right, I had 2 iodines here. I need 2 here. And that gave me 2 sodiums. 2 sodiums, it gave me 2 nitrates, and I had 2 nitrates. All right, what do you think? This is a little higher level of chapter, isn't it? We know it's double replacement, but this double replacement works because of the formation of a solid. And that's called a precipitate. That's why it's called a precipitation reaction. All right, what do you think? Is that okay with you? All right, I gotta go. You have to go, actually. Yeah. All right, remember the homework thing I gave you? You can start that anytime you want, okay? So if you want to go home for 10 minutes tonight, I said, I'm gonna look at that homework pack and see if there's any of that I can actually do. All right, thank you very much. All right, bye.
Here, can I turn in the notes for like that video and whatever?
Okay, good. So, I don't know if the thing I did today, that make a little more sense when we were talking about hydrogen bonding and being a polar molecule. Okay. Anyway, it was just amazing to me. It makes surface tension, it makes adhesion, cohesion. It makes things, it boils at a much higher temperature than it should. It's actually a liquid in a long range temperature. Did you remember thinking about specific heat? It has one of the highest specific heats, meaning it takes more energy to raise the temperature of water. So a little piece of metal, get a little energy, whoop, temperature goes way up. How about water? You know. And so, and we're made of water, and we give off heat all the time. So we don't cook because we're made mainly of water. All right, thank you. Wait, I'll put your name on it. You do? Okay, thanks.